Okay, yeah.
Hey everyone, we don't have our usual host, but here today we have Chirag to talk about calibration for binary systems.
Hi, so I'm Chirag. I work with Aditya Ramdas. I'm in my final year in the ML department. So I work on calibration, and that's what the talk will be about today. So calibration is basically a problem of making useful forecasts for binary sequences. So let's say you have a sequence of outcomes, and this is an infinite binary sequence. You want to produce some useful forecasts for this sequence, which are essentially some kind of probabilities for each element of the sequence. So you can essentially think of like the ideal goal is that, the probability of yt equals 1 equals pt. So just a binary sequence, if I give you a probability, that's essentially the most you can know about the sequence, assuming it's randomized. And the goal is to produce useful forecasts. But of course, in practice, we won't know the actual probability. So we want something that's a bit weaker, but still useful. And that's where calibration comes in. So informally, calibration is as t goes to infinity, or as you go further and further in the sequence, you want that the average of the yt's on instances where you predicted some particular p equals p. Okay, so the canonical example here is like rain forecasting. So let's say I say 30% chance of rain on 100 days. And then I say 30% chance on 1,000 days and so on. So in the long run, I want that on 30 out of those 100 days, I actually see that it rains. And on 70 days, I see that it does not rain. And it shouldn't be more or less. Because for example, if the chance is just 10%, maybe you decide not to take your umbrella because you're like, I don't want to carry the umbrella. I'm okay with the 1 in 10 chance of having rain. But what if that 1 in 10 ends up being like 3 in 10? On the other hand, if you said 5 in 10 and you took your umbrella and it did not rain because it's actually much higher than what the true probability was, you'll be annoyed. So of course, there's obvious implications for machine learning where you want to predict scores, probabilistic scores for your classes. So that's the broad intuition. So the average of the y's or the outcomes in the long run should be equal to what you predicted on those instances that you predicted p. Okay, so I'm just going to simplify this this problem a little bit before defining a formal goal, and also defining like what's the setup in which you want to achieve this goal. So for example, hypothetically, suppose you somehow knew the outcomes before forecasting, then you would just forecast the outcome itself as your probability, right? So it depends on what the protocol is to define, like to understand whether you can actually be calibrated or not. So let's just simplify the goal a little bit first. So instead of saying that I'm going to be forecasting on the entire real interval between 0 and 1, I'm just going to say that all I care about is some 2 epsilon discrete forecasts. So this is a 2 epsilon grid. So I'm going to essentially, what I'm saying is that I want to forecast this interval. And I want the long-term probability to lie within this interval. Okay, so all I care about is so I'm going to forecast the midpoints of these intervals. I'm going to call this M1, M2, and so on till M. So let's say there's M intervals where M is 1 over 2 epsilon. And I'm going to assume that this is an integer, like epsilon is say something like 1% or 0.01. And then this would be 50. So you have 50 different bins. And I'm going to say that my PT should be, instead of 0, 1 to infinity, it should just be in the set M1, M2 through MM. So that's my forecasting set. Okay. And then the goal, so now the goal is going to be So so I take an average over all the different intervals or bins that I'm going to be forecasting. And I look at the number of times I forecasted until, say, time capital T. So NIT is number of times PT equals MI for T less equal capital T. Okay. And then PIT is the observed average until time T. So it's the average of YT given T less equal T, PT equals MI. And it's possible that you never forecasted MI until time capital T, in which case you can just set it to MI. But it won't really matter because your NIT will also be 0. So it won't have a contribution. No matter what you set PIT to, it won't have a contribution in this term. Okay, so this is an average calibration error style of term. This is the error I got. So I was forecasting, say, 75%, which is MI, but the true probability was 30%. So I have an error of 0.45. And then how many times did I actually make this error on average? So it's the number of times I forecasted that interval. Okay, and now because you have this epsilon grid, I'm going to allow a little bit of slack. So I'm going to say, I'm allowing you to make errors up to epsilon. And this whole term will I'll just call this the epsilon calibration error. Okay, one more thing. So if somehow you were doing better than epsilon, you don't suffer an error. Let me just make this bigger. Okay, and then the goal is that this should be little o of 1 in terms of the dependence on T. So I'm treating epsilon as a constant, like 1% or something like that, which means the number of bins is also a constant. And I'm just seeing what happens as T goes to infinity. Okay. So does this any questions so far? Yeah.
Is the max supposed to be outside the sum? So if you get a negative loss at some points, it compensates for positive loss at other points? Or is it supposed to be inside the sum?
No, yeah. Yeah, so I'm doing it for, on average, I'm giving a slack of epsilon. You can ask the question if each of these were, so you say like max of this minus epsilon comma 0, which would be a slightly different question, but this is sort of the easiest to deal with. So those two are different entities. I'm going to be talking about this. Yeah. Yeah, just to be clear, this is like the minus occurs outside. Okay, so the sum is here and then the minus occurs there. Okay. Yeah.
What's the assumption on Y1, Y2? Do they have to be?
Yeah. Yeah, so let's talk about that. So now I haven't defined who's going first and who's like what is probabilistic and what's not. So whether or not you can sort of achieve this goal depends on what protocol you're following. So let's define protocol 1, which is that nature or sort of the outcomes happen after the forecasts. So let's say at time t equals 1, 2, and so on. I forecast PT and I observe YT. Okay. And when I write this protocol, it means that at any time, so these are two players, you can think of this as nature and this as the forecaster. And at all times, the previous moves of players that have gone before are available, which means that in particular, like YT sees PT, YT minus 1, PT minus 1, and so on. Okay. So I'm just going to erase this, but basically everything is being played sequentially and everything is known. It's public knowledge once it's played. Okay. So now in this setup, there's no randomization. It's just a game. So I'll just pause for a second because so you can kind of determine whether you can actually forecast in this sense or not. It's not that hard to see, but I'll just pause for a second if you want to stare at it. But I mean, it's a theorem, but it's kind of well known. But the point is that you can show that nature can force the epsilon calibration error to be omega of 1. Which means you can't be calibrated in some sense. You can't get this. And the proof is very simple. You just say nature just sets. If somebody wants to take a guess at it. Okay.
Yeah, one T is just one and PT is a half of us.
Yep, exactly. Yeah.
So just to make sure as long as
epsilon is smaller than 0.5.
Okay.
Or maybe 0.55 or something. Yeah. So as long for small epsilon, that you will essentially, so if you do this, then this term is always going to be at least 0.5, because whenever you forecasted something less than 0.5, your PIT is just 1. You always showing, nature is always showing ones. And if you forecasted something greater than 0.5, PIT is always 0. Okay. So this is simple, I guess. It's like a sort of philosophical step more than actual useful result. So now let's see what we can do to save this notion of calibration. And the reason this setup is not completely meaningless philosophically is that if you let's say you want to forecast the probability of rain, you can't assume that that rain is being generated from some probability distribution. So one modeling assumption you can make is that rain is actually adversarial. It sees your forecast and then produces an output. And in online learning, if you're thinking about regret, you can actually show that you can have small regret even for such adversarial sequences that don't even that exactly see your prediction. But let's consider a different setup. So now what I do is I allow the forecaster to randomize. So I say the forecaster predicts some UT, which is a distribution on this output set. So over all these midpoints. Okay, so it's a distribution over all the bin midpoints. Now nature sees this random distribution and reports some outcome, and then forecaster draws PT from UT. So at this point, this is just a natural draw. There's no strategy. There's no strategic elements at this point because you've already said UT. You're just going to draw PT from UT. Okay, so instead of having a fixed forecast, I just have a random forecast. So now you can imagine like a similar strategy to something like this. You can say that nature sees UT and then sets YT to the expected value of PT. Right, there is some expected value of PT under UT. And that could be lesser or greater than 0.5. Based on that, nature plays something like this. So it's not obvious that this actually gives the forecaster some power. But this is kind of, so this is a seminal paper by Foster and Warren in 1998, where they, I won't pause here because this is if you know this, otherwise you're not going to just think it through. It turns out that you can show that the expected, so the forecaster can devise a strategy such that the expected epsilon calibration error is 1 over square root p. And at this point, we know a bunch of proofs for this. One is through something called internal regret. And there's another one through Blackwell approachability. But there's a few more ways we can see this. So this is a 1998 paper that people did not knowing this, people did not expect that you can get calibration just using randomization. So this kind of started a lot of work in understanding the relationship between calibration, regret, and something called Blackwell approachability. So I'll just briefly mention these two things if you've seen, because some of you may have seen them before, but I won't go into the details. So the proof through internal regret essentially goes through saying that if I were playing M1 and I could have swapped my action for something better, then that better thing would be calibrated, because what do I care about? I care about what's the observed outcome so far, and its difference from what I've predicted. So I can always predict something that's the closest interval to the observed outcome. So by doing that kind of swap, which is also called internal regret, I can provably get down my calibration error. And then if you can essentially minimize internal regret, you'll get small calibration error. So that's the internal regret proof idea. And then the Blackwell approachability is basically a vector generalization of von Neumann's theorem. And here the actions that you're taking are these, and then you get a vector reward, which is how far you are from each interval. And then you can show that you can go into the interval. So there's some kind of a vector valued space where you're trying to converge to a certain so a certain region of that space, and you can actually do it under a particular algorithm. Okay, and then yeah.
Sorry, I have a question. First of all, is this true for all epsilon greater than 0?
Yes.
You can achieve this, but maybe the O depends on the epsilon or something?
Yes.
And the other question is, you gave the very simple algorithm of just doing it based on the expected PT being above 0.5. Is there a simple way to state what the algorithm is in that case? Is it already complicated?
So what it's going to end up doing is kind of hedging between close points around 0.5. So it'll say 0.45 and 0.55 with some probability. And then that's essentially going to force, no matter what nature does, 0 1, you can't be too far away. So if nature actually shows you a lot of ones, then you can move towards 1. But if nature is actually kind of completely being adversarial and playing that yt equals indicator of expected value is equal to 0.5, then nature is going to be forced to be close to 0.5 on the long run itself. And you're predicting close to 0.5 as well.
So you started 0.45, 0.55, and then you moved to 5.565 if nature
If,
comes to the ones, and you sort of gradually approach.
Right. But that hedging is essential to actually show calibration. Okay, and then we showed that this is actually tight using the reduction to Blackwell approachability. So this is it's not a very surprising result. We showed it formally, but it's kind of an expected result once you understand sort of calibration. Blackwell approachability implies calibration is well known. The other direction is a little bit technical, and then you actually have to use some particular lower bound for Blackwell approachability to get this. Okay, but today I'm not going to be talking about this. I'm going to be talking about a different setup where you can actually get much faster rates. So this is kind of background, but I'm going to be going into the actual algorithm and the proof for this different setup where you can get a much faster rate. So any questions so far? Okay, so we defined a new protocol. So we said that at time t equals 1, 2, and so on. So we allow the forecaster a little bit of wriggle room. So forecaster either predicts So forecasters are allowed to say just a single MI, or they're allowed to say a small interval MI, comma MI plus 1. They're allowed to give two nearby points as their prediction. So in this figure, instead of putting all its mass or randomizing over these midpoints, I'm allowing the forecaster to just say, this is my interval of forecasting, or these are the 2 points that I think will actually be calibrated. So let's say like in practice, you're not really sure what the true probability of rain is going to be, but you're okay to say something like 66 to 67%. Or if your epsilon is higher, maybe 70 to 75% or something like that. And that's arguably a very useful forecast. That's something you can still act on. But there's this uncertainty which you don't want to completely remove. You still want to keep that around. So I'm allowing the forecaster to actually report that. Okay, and then nature looks at this forecast and gives you some YT. Okay, same as that, but now it's deterministic. I'm not randomizing anymore. I'm actually giving you this interval. And then, okay, so now the forecaster said 2 things. How do you judge that forecast? So you give them a little bit of wiggle room. You say that they're allowed to set PT to MI if YT equals 0, and they're allowed to set PT to MI plus 1 if YT equals 1. Okay, so if the actual outcome was to the left or was 0, then you're allowed to actually say that my forecast was MI. I was saying 65 to 70%, but actually I meant 65%. And then if it's 1, then you're allowed to be like, okay, actually I meant 70%.
Is this strictly better to always say interval for the professor?
As against this?
Yeah.
Yeah, so it is strictly better. In our algorithm, it's just simpler that sometimes you can say this, but yes, you're always going to get a benefit. Even if you somehow wanted to say a particular MI, you can always be like, okay, MI plus 1 or MI minus 1 MI. And that's going to be better, but the algorithm that I'll describe, you actually do say MI sometimes. Yeah, you can also think of this as like saying MI, comma MI. So you're kind of forecasting an interval of which just contains MI, or an interval that is MI, comma MI plus 1. So like you have to forecast an interval with 2 epsilon width. It could either be just a single point or 2 consecutive midpoints. Okay. Okay, and then for this this setup, I'm going to show that this is actually, so let's remove these maxes. So I'm going to show that the forecaster can deterministically satisfy, this is O1 over T over here. So I actually write down the exact rate. So up to constants, it's actually M over T, where M is the number of pins. And in terms of epsilon, it's 1 over 2 epsilon T. Okay, so that's the rate that I can actually show, and it's much faster than this one. So you get like this 1 over T rate, which is essentially you get constant error over time. You're not accumulating error at all. And a quick note, like, so this essentially means that if you set epsilon to 1 over square root T, then you get this term itself is 1 over square root T, and then you can use a doubling trick to get bounds on this term itself without caring about epsilon.
In the what was the dependency on epsilon?
What was the word?
The dependency on epsilon, or on was it like Logan?
No, it's this on epsilon. Yeah, so they get epsilon plus 1 over square root epsilon T, and then epsilon equals T to the minus 1/3 is sort of the right dependence. So you get what is that? Yeah, that works out. Okay. So this is the rate, whereas we get 1 over epsilon t. And there you have to set. So if you don't want to treat epsilon as a constant, you get t to the minus 1/3. Whereas in our case, you'll get t to the minus half. Also, their thing is an expectation. So then you have to actually, if you want a finite sample, high probability kind of bound, then you have to do some more stuff. But in the end, you get something like that. Whereas ours is deterministic. Okay, so that's the background and the setup. Now I'll actually describe the algorithm and prove that it works. Any questions on the setup? I think that's, yeah, so I have 25 minutes for this. Okay, so to describe the algorithm, I need 2 more definitions. So and let's just define everything for like little t, which is generally any t less equal capital T, because I want my final result for capital T that's some fixed horizon. So I'm going to define something called a deficit. Sorry. Okay. So this is something called a deficit. What it's trying to capture is that if I've been forecasting MI at a number of instances, but it turns out that my left, so I haven't defined LI, sorry. Okay, so let's call this L1. So I'm going to call the left endpoints of every interval as the LIs. And the right endpoints as the MIs. Okay. So essentially, Li equals L1 equals 0, L2 equals 2 epsilon, 4 epsilon, and so on. And then R1 equals 2 epsilon. So R1 equals Li plus 1. Ri equals Li plus 1. Okay. So left endpoints, right endpoints, and midpoints. The deficit is how much below I am than what I need to be. So the outcome so far, they're smaller than Li. So assuming the deficit is greater than 0. And it's like how much smaller I am than I need to be. So my hope is that DIT is less equal 0 eventually, which means I'm on the right side of where I need to be with respect to this interval. I'm calling it a deficit because the outcomes are in deficit. And then the flip side is the excess term, which is how much further to the right am I than where I should be. Okay, so let's say you've been forecasting the second interval and your PT ends up being here, then you'll have an excess, which will be equal to this delta. And if the PT ends up being over here, then you'll have a deficit, which is something like this. Okay, so these definitions are kind of important. They're going to keep coming up. If there's any questions you can ask. Okay, and now we're ready to actually define our algorithm. So at time t equals 1, I just say E1 equals M1, something arbitrary. And then in the future, I could have one of 2 situations. So if there exists an I, which is a good prediction so far, which means that there is no deficit and there's no excess, then just set PT equals MI. Okay, so this means that I'm on the right side of the interval with respect to both the endpoints. But if there does not exist such an I, then find an I from, okay, this notation just means it's 1 through m, and this means it's 1 through m minus 1, such that there is an excess for I, but a deficit for I plus 1. Okay, so I'll show that you can always find such an I, but the intuition is that so if you're not on the right side of every interval, there's got to be some interval where you're saying more than what you should have said, and for the next one you got to be saying less. So I'll prove that in a second. But then if there are two such intervals, I can actually play both of them and hope that whatever happens, I actually improve the error for those intervals, which means I'm going to then say mi comma mi plus 1. Or in other words, I said pt to mi if yt equals 0 and pt to mi plus 1 otherwise. Is this visible? Okay, cool. Okay, so any questions on the algorithm? So there's one big question. How do you find this? And I'll prove that in a second.
What does this do on time step 2? So at time step 2,
Yeah.
only one thing has ever been predicted. So clearly everything else has 0 deficit. So this is not satisfied for anything.
So at time 2, let's say you observed 0, which means that the first interval is fine. You're going to get di less equal 0.
Let's say you observed a 1.
Let's say you observed a 1, which means you have an excess for the first one.
And you have no deficit anyway.
And no, wait. So at time step 2, these two are going to be satisfied for I equals 2.
Oh, okay. So try every
Because-
one of these ones.
Yeah, you'll play all of them, right? So well, if you get a 0, then you might just play 1 again. But otherwise, you'll play all of them once to sort of initialize these, and then you'll start playing this. So yeah, but that's a good question. So let's say so now you predicted I equals 2, and you saw a 0, which means you now have deficit for 2. Then you can play this. Okay, let me use this. Okay, so let's first just prove that this is a valid algorithm. That you can actually find case 2. So let's say case 1, let's call this case 1 and case 2. So let's say 1 does not hold. Then I want to show that you can find I. It's not too hard to see. Okay, so first observe that D1T is the deficit for the first interval, which has Li equals 0, L1 equals 0, and P1T is obviously greater equal 0. That means you would have the deficit at all times for I equals 1 is going to be less equal 0. And similarly, the excess for the final interval is going to be less equal 0. And because this condition is not satisfied, you have a greater than 0 here. Otherwise, you've found your I. Okay. So this means that at some point, you're going to see a flip. You're going to see that you had a less equal 0 here and a greater than 0 here. Okay. Because you had greater than 0 initially and you had a less equal 0 eventually. So this is by definition, and this is by assuming that 1 does not hold. Okay, so you have this flip. Now, what's happening over here? Well, this condition 1 does not hold again, which means that you must have greater than 0 here. So this is I, and this is my I plus 1. So I have greater than 0 for excess and greater than 0 for deficit. Okay. That's it. That's the proof that you can find such an I. Any questions? Because I might erase this. I'll keep it around. Okay. Okay. And now, okay. So now the algorithm works. My goal is to show that summation I equals 1 to m I t over t. Okay, so I'm actually going to prove all of this. So there's going to be a bunch of math from now. Okay, so first let me just simplify this particular deviation term or error term for interval I. So observe that this is equal to epsilon plus so this is like a lemma. And the proof is easy. Again, you can see it by picture. So let's say this is a particular interval, Li, Ri, and this is your Mi. So you care about the distance between what you're observing and Mi. And remember that these are epsilons. So now let's say that PIT ended up being over here. Okay, so this is the left-hand side equals this, right? And what's the right-hand side? It's just epsilon plus the max of the deficits and the excess. Obviously, you have an excess here. So this is exactly equal to EIT. Okay. Now let's say PIT was here. It's to the left of Ri, but to the right of the midpoint. Then this is negative, but it is the excess, and it's the larger of these two because the deficit is negative, but it's this high. So the excess and deficit can be negative if, and then in particular the negative if you're inside the interval, but this one's going to be smaller. So again, epsilon, which is this, plus this negative term is going to be your miscalibration. And then the same kind of proof goes through for the deficits. Okay. So, okay, so this holds. And then, so what's this then? You have summation I equals 1 to t and IT over t. It's okay. And now this part is just equal to epsilon. And this remaining part I'll argue about. So this is just equal to epsilon plus plus summation I equal to m. And RIT is okay. So yes, I am missing a divided by t. Okay. Yep. Okay. So the idea is that basically what I'm trying to show is that for every interval that I've forecasted, I'm keeping track of how far I am from this interval. I'm removing this epsilon term. Like if you were inside this interval, I'm giving you some slack, and then I'm seeing how far you were. So like if you were here, this is what I'm going to be kind of bounding. Or if you were here, this is what I'm going to be bounding. And in the end, what I'm going to show is that RIT is less equal 1 at all times. And that's going to complete the proof because this is then just m over t. And that's what I want. So at all times, you can be at most you can be at most a small distance from the actual interval you want to be. And that small distance is shrinking over time as you're predicting more and more. So it's actually just going to be 1 over NIT, the number of times you predicted that interval. Yeah.
Is this equivalent to just saying we're never more than one guess outside the interval?
Yes. Right. So at all times, you're never more than, if you could flip the sign of one of the bits, then you'll come inside the interval. Roughly speaking, eventually. So if you have just a single bit, that may not be true. Like if you're here, then both 1 and 0 are out. But essentially, it's that if you can just flip one bit, you'll get into the interval. Okay, so I'm going to be proving this claim that RIT is less equal 1. So I guess theorem or lemma, whatever, is that. So at all times t, and for all intervals I, you have RIT less equal 1. And I'm going to be proving it by showing that RIT either stays bounded by the previous value or 1. So these are equivalent essentially, but it's not too hard to see. But like this is the proof technique. I'm just going to induct then on RIT. And then it's going to imply this, which will complete the proof. Okay, so let me just draw a line. These things are getting messy. Okay, so I'm going to show that the residual at time t plus 1 is at most what you were seeing before and 1. Okay, any questions so far? Guys, you have 10 minutes to complete the proof. Okay. Okay, cool. Okay, so basically I need to argue this for 2 different cases. One is if I was already doing well and I predicted just that interval or just that MI, just the midpoint of a single interval, or I was not doing so well and I predicted 2 nearby midpoints. So the easier case is obviously this one. So in case 1, which means that at time t, I saw DIT and EIT less equal 0. I predicted ET equals MI. And I want to show that RIT plus 1 is less equal to this. Yeah, so notice that if I don't actually forecast or predict MI, then the RIT value does not change. So I'm only going to show this for the I which is actually predicted, otherwise it's just equal. Okay, so I want to basically now show that and this is exactly RIT plus 1. Okay, so in this case, I'm not going to compare it to the previous value. I'm just going to show it's less equal 1. And okay, so to see that, observe that these two. Okay, so you had a deficit at time t. So you were inside this interval. And now I'm going to say that no matter what you observed, you can't go too far out more than the number of times you've predicted that interval, which kind of intuitively makes sense. You can't move by more than 1 over the number of times you predicted that interval. The average can't move by that much. So formally, since I have DIT and this less equal 0, I can say that this is less equal NIT plus 1 times so each of these are less equal 0. So if both of them don't move by a lot, or in other words, if both of these are smaller than 1 over NIT plus 1, then I'll have shown this. Okay, because these are less equal 0. That's the important point. If these were not less equal 0, I would have essentially have this plus NIT plus 1 times max of DIT, PIT. But these are both less equal 0, so I don't care about that term. And that's my case assumption. Okay, and now what are each of these? Both of these are just essentially equal to how much did your average change when you went from time t to time t plus 1. So it's just PIT plus 1 minus PIT. And at this point, many of you can probably, you trust me that the average does not change by more than how many times you've predicted so far, but I'll just prove it formally. So I'm just going to write PIT as this is PIT plus 1 minus PIT, and that's exactly equal to YT minus PIT divided by NIT plus 1, and then this is less equal 1. And that completes the proof. Okay, so any questions about this step or this step? Okay. So either everyone understands everything or everyone's very confused. I hope it's the former. Okay, cool. But so if by chance you're still confused and no one asks, it's just essentially saying that the average won't change by a lot. Okay, so you have this. Now let's argue about case 2, which is a little bit more involved, but it's also very simple. Like the proof of this main result in the paper is like 1 or 1.5 pages. Okay, so case 2 is that you have you had EIT greater than 0 and DI plus 1T greater than 0, and you predicted MI, MI plus 1. And without loss of generality, let's assume that you then observed YT equals 0. So it's not very completely obvious that this is a without loss of generality assumption, but it kind of goes through. So you observe YT equals 0 and you predicted PT equals MI. And for this I, you had EIT greater than 0. Okay, those are the things that I will need. And then the same argument would go through if you had YT equals 1. Okay, so what's happening in case 2? It's basically saying that what this algorithm is kind of knows that over time what's happened is that the true average for this interval, let's say, was above what it should be, and for this interval, it was below what it should be. And what I've done is I've forecasted these two, and I've instantiated the lower one because I saw YT equals 0. So the average here was like somewhere here. This was P2T, and I forecasted this because I saw YT equals 0, which means that this is going to move to the left, and it's going to decrease my R term, my RIT term. Okay. So basically, so now I have to. So let's say that you continue to have an excess, or the. So let's say that NIT plus 1 times max of these two actually equals NIT plus 1 times EIT plus 1. Okay. Okay, so I'm just writing down the definition of EIT plus 1. It's just this. Now, what's the product of these two? It's the number of times I observed Y equals 1 in my current sequence, which is exactly what I did at the previous step, plus whether yt equals 1 or 0, right? So essentially this equals this. And here I have nit ri minus ri. So it's nit plus 1 times ri is just nit ri minus ri, because I'm actually forecasting I. Okay. So here I'm going to use that this equals 0 to get that this is less equal. This is less equal nit times okay. So now what's this minus this? That's just EIT. That's exactly the definition of EIT, and it's essentially exactly the error that I got at time step t. And that's what I want to show. I want to show that this is less equal to previous residual or previous capital R value minus this Ri. So it's less equal. So this implies that RIT plus 1 is less equal RIT. Okay, so any questions about this? I kind of did a bunch of equations, but it should be clear. If it's not, just ask me. Okay. Okay, so this is actually the tricky one. The other is easier. So here I assume that the max actually instantiates to EIT plus 1. And let's say that it was the other case. Okay, so what this is saying is that you somehow started with an excess for interval I, and then you saw yt equals 0, and it went all the way back to a deficit. So somehow this pt was an excess. It did not move a little bit. It went like all the way over there, which is possible essentially only at small t's, and it reduces to this argument, and that's simply because like so now. So this is less equal nit plus 1 times dit plus the maximum that you can move. And then this is less equal 0. Okay, so why is that less equal 0? Because I had an excess at time t at the interval I, so I must not have a deficit. That's just less equal 0. And this I've already bounded over here. So I've already shown, so essentially, if you're somehow switching sides, you're going from an excess to a deficit, you can't switch more than the number of observations so far, or the number of times you predicted pt equals mi so far, because averages can't move that fast. So this is just less equal 1. This is less equal 0. This is less equal nit plus 1. Sorry, 1 over nit plus 1. Okay, so that's the proof. I'll just like summarize what's happened so far. You can ask me questions. So I found an interval where either you were already doing well, which means the average can't move too much, whatever the true outcome is, or I was not doing well. If I was not doing well, I forecasted 2 intervals such that for one of them, yt equals 0 will help, and for the other one, yt equals 1 will help, because you're going from large to small or small to large. And then I actually argued that in that case, you can actually show this this lemma essentially, which gives you that this error is small. And as you mentioned at some point, it basically means that for every interval, I have at most an error of 1. Cool, that's the proof. Any questions?
So you are saying other forecasters don't have to care about the forecast?
Yeah, that's a good question. So it turns out that you can be calibrated without actually caring at all about what's about your covariance, about your information. But what will end up happening is that, let's say the average number of days that that it rains is 70%. You'll just end up forecasting 70%. You're not conditional on the days. But there are techniques you can use to sort of lift this basic adversarial analysis to cases where you have covariates, and then you can be calibrated to adversaries while using that covariate knowledge. So now you will effectively, in practice, you'll see that you're predicting different probabilities, and you're calibrated for all of them. So this is, yeah, in
So
principle, yeah.
You can get maybe better rates if you're using information than what is calculated.
Actually, no, you won't get better rates. You might actually get a little bit worse, but but you'll be more usefully calibrated. So calibration is kind of saying that you don't need to sacrifice being correct in terms of probabilities to actually be useful. Like you can always get the right probabilities if you have some kind of information. Yeah.
So I guess you are saying we need to like sort of look at a trade-off between, let's say, logistic loss and also the calibration.
Yeah. So actually, the logistic loss has a calibration term inside. So this calibration term kind of falls out of the Brier score loss, and similarly for the logistic loss, you can have like a calibration term that falls out. Sort of minimizing, so you can't minimize the logistic loss to 0, but you can minimize the calibration loss to 0. Then there's like this entropy term in the logistic loss. It's a very technical answer, but I don't know if that answers your question. So there's like some term that you can't reduce. That's essentially the term about comparing to the best forecaster in hindsight. And then there is a term that you can reduce, which kind of is the difference between, so it's kind of like a regret analysis type thing for logistic loss.
I see.
Yeah, but it's not exactly that.
So this analysis was very one-dimensional, right?
Yeah.
If I wanted to define a two-dimensional version where I was predicting some joint distribution, would I, like, this technique doesn't, would this sort of technique work if I was trying to do a multi-dimensional version?
Yeah, so I haven't derived yet. This just came out like this year. So yeah, my advisor wants me to derive the multi-dimensional version for this. So if you want to do it, that'll be awesome. We can do it together. But for the regular randomized game, you do have multi-dimensional analogs, so you can get calibration in multi dimensions. The big problem is that all of these adversarially calibrated algorithms depend on this grid, and as you have more labels or larger outcome set, that's going to grow exponentially. So you can be calibrated once you've defined your bins or intervals. But your dependence on the number of bins is something like it's growing as m or square root m or something like that. And that's exponential with more labels. So in theory, yes. In practice, it's a harder problem. So in practice, you want to be calibrated for some useful subset of labels, but not all of the labels. Okay, cool. Thanks for listening.